Hello, so let's have a look at capacitor discussion. So in the previous model, we have seen various types of capacitor as shown in the pictures. And you can see they come in a variety of sizes. And capacitor is a two-terminal electrical passive component, and the symbol of is shown over here. So there are different ways to show the capacitor. The first one here is called as fixed capacitor. Again, it has two terminals, two plates, and it is called as a fixed capacitor. If you see the symbol like this where the polarity is indicated right over here, so it is called as polarized capacitor. So generally this type of capacitor, that is electrolytic, that is called electrolytic capacitors, they are polarized capacitor. It means their one terminal is positive, marked as positive, and then you have a resistor. Just like a resistor, variable resistors, you have variable capacitances. It means its capacitance can be varied. So that's an electronic symbols for your capacitors. Now let's have a look at the internal structure of the capacitor and how it works. So let's have a look at the theory of operation. So again, as you can see right in this picture, there are two plates of the capacitors and there are two terminals. So here, that's the one plate and that's the second plate to hold the charges of opposite polarities. So plus Q indicates the positive charges on that are deposited on one plate of this capacitor, which is this plate. And the negative Q indicates negative charge carriers which are deposited on the other plate of the capacitor, and in between of the capacitor it's called as dielectric. So in between the capacitive plates there is a material called as dielectric. It can be paper, plastic, or even just an air. So capacitance based on this structural representation can be defined as C equals to epsilon 0 epsilon r multiplied by area of the plate divided by the distance between the two plates. So epsilon 0 is the permittivity of vacuum and epsilon r is the relative permittivity of the material. A is the cross-section area between the two plates. So you have a plates, and just like shown in this picture, you have these two plates, and in between there is this dielectric material. So A is the cross-section area of individual plates, and the D is the gap separating the two plates, or the distance between the two plates. So when you actually apply a voltage across the two plates of this capacitor, so the charges are created on the two plates of the capacitors according to Coulomb's law. So there are opposite charges, and due to which an electric field is generated, or electric force lines are created, which are shown in the color blue here, and that exerts a force from positive charge to the negative charge. So that's basically a Coulomb's law. And in the orange you see that there is a dielectric material, and because of this dielectric, the charge separation in this parallel plate capacitor causes an internal electric field, and the dielectric as shown on in orange reduces this field and increases the capacitance. So if you have a dielectric material which has a high dielectric constant, so you see the capacitor is going to go up. So internally the electric field gets reduced and the capacitance gets increased. Now let's have this equation as we've seen this in the previous models. Please refer to that. So C capacitance, net capacitance, is equal to Q over V. So if you apply a 1 volt across the capacitor, if it creates a charge positive Q and this is negative Q, charge of 1 coulomb each on each of these plates. Again, if you apply 1 volt voltage difference across the capacitive plates, and if it creates a charge of 1 coulomb on each plates. So then net capacitance would be 1 coulomb divided by 1 volt. So it is called as 1 farad. So that's the definition of the capacitance, how this equation can be utilized and understood.